Hello, welcome back. This will be a short video explaining how we can describe functions. We have some experience describing continuous functions. The main ways that we do that is in words. We can talk about taking a number and then squaring it. We might give a formula for this function, f of x is equal to x squared. And sometimes we will draw a graph of a function as a way to describe it. Here's a graph of the same function. Often we're using formulas and graphs because they allow us to convey information about uncountably many inputs and outputs. So no matter where we are on this number line here, we would be able to figure out what the value of a function is, or no matter what x is, we would be able to get a value for the output of that function. When we describe discrete functions on small finite sets, often we'll rely heavily on this idea of writing it down in words. Here's an example. For a numerical input, 1, 2, 3, and 4, the output is the number that comes next in an alphabetical order, wrapping around from Z to A. Okay, that's a mouthful. Let's try to parse that and understand what's happening. We have 4 numbers written out in words, and what we'd like to do is we'd like to write them in alphabetical order. So if we do that, we have 4, 1, 3, and 2. And so this function takes 4 in and gives out the next number in alphabetical order, which is 1. If you take in 1, the next number in alphabetical order would be 3. If you take in 3, the next number in alphabetical order is 2. And then there's no next number after 2, but we're going to wrap around and say that if 2 is the input, then 4 is the output. So now we better understand what this function is. Other ways to represent this function is as a table. We can take the inputs and the outputs and we can write them down. That if 4 is the input, 1 is the output, and so we would put the 4 in the in column and 1 in the out. Now something that will be especially helpful is to draw these as arrow diagrams. When you have a finite number of terms, you can put all of the elements in the domain ordered in some nice order on the first row. You can then put all of the elements in the codomain here in the second row, and then you put arrows in here that keep track of the output that corresponds to each input. So for example here, when the input is 4, the output is 1, so when the input here is 4, it should have an arrow connected to 1. This diagram can be a bit confusing, so another way to draw the same picture is to straighten out the arrows. The result of that is called two-line notation. We keep the top row the same, and in the bottom row we put the corresponding outputs. So because 1 is the output of 4, we put 1 below 4 in this two-line notation. For continuous functions, we had both graphs of functions and formulas for functions. What does that look like here? So what is the output for the input 1? Well, we can read from our two-line notation that the output is 3. For the input 2, the output is 4. For the input 3, the output is 2. And for the input 4, the output is 1. And so this picture is the graph of the function that we had above. The important thing to recognize is that you should not connect these dots because there's nothing between those numbers 1, 2, 3, and 4 in this picture. We can also ask the question, what's the formula? Well, the best way to write this is probably with a piecewise defined function, where we have when x is equal to 1, f of x is 3. When x is equal to 2, f of x is equal to 4. When x equals 3, f of x is equal to 2. And when x is 4, f of x is equal to 1. Okay, that's it for now.